So we have an electric resistance heater is embedded in a long cylinder of diameter 30 millimeter. When water with a temperature of 25 degrees and velocity of 1 meter per second flows crosswise over the cylinder, the power per unit length required to maintain the surface at uniform temperature of 90 degrees is 28 kilowatt per meter. On the other hand, if we have air at 25 degrees, but moving with a velocity of 10 meters per second, the power per unit length required to maintain the same surface temperature is much larger. We need 400 watt per meter. Calculate and compare the convection coefficients for the flows of water and air. Already from the given, we can expect the results because even if we have a much higher velocity for air, the value of the power needed to maintain a constant temperature is much larger than the one for water. And this is due to the high convective coefficient of water compared to air. And we can calculate this by equations. So the idea is the following. Whenever you have a surface, and this surface is exposed to an airflow, in case the temperature of the surface is larger than the temperature of the airflow, you will have heat loss by convection from the body towards the fluid. And since you want to maintain a constant temperature, this is not possible if you don't have internal generation. So what will happen here, you need to have a power that is supplied to maintain your surface at the temperature that you want. And the question is to find what are the convective coefficients of water and air, knowing in each case what is the power per unit length that we are using. So whenever you have such problem, try to write the energy balance equation because you know that nothing is lost. So at the end, the heat that you give to your system, since you have steady conditions, so you don't have variation with time, heat that you are giving to your rod, okay, or cylinder will be lost by convection, and this will ensure a constant temperature at the surface. So all we can write is that in this problem, if you want the power that we are supplying, so Q supplied is equal to Q convected, okay? Now, since they gave us the power per unit length, so we can do all analysis per unit length if you want, okay? So you can say that Q prime, which is the value of supplied power per unit length, is equal to Q prime of convection. And Q prime of convection is Q convection per unit length, so over the length of our cylinder. We know the formula for convective heat transfer. So we can say that Q prime, let us start with the flow of water, okay? For the flow of water, Q prime is 28 kilowatt per meter. So Q prime needed in case of water flow is 28, is equal to, the convective coefficient is H, the convective heat transfer is given by the convective coefficient H times the area of contact, if you want the area exposed to convection, which is here. To know it, you just have to draw your geometry. This is your geometry. You have a cylinder and you have a flux over your cylinder. So the lateral area is the following one. So this is the lateral area that is exposed to convective flux. And to calculate it, all we have to do is to consider the diameter as a perimeter, sorry, times the length. So it's 2 pi r times L. So times, of course, delta T, which is the difference in temperature between the ambient air or ambient water, which is T infinity, minus T surface. Now, should we do T surface minus T infinity or T infinity minus T surface? It depends on the flux direction. So here we know that we are losing heat. So the flux is going from the surface towards the fluid. This is why delta T here will be T surface minus T infinity. Everything is provided for us. So if we start with water, we know that T infinity is 25. So we can replace here T infinity by 25. The temperature of the surface to maintain, we want to maintain it at 90 degrees. So for Ts, it's 90. Now, as we mentioned, we want to determine the flux per unit length. So we should divide A by L. And as you can see, if you divide here the convective area by L, you will just get 2 pi r, or pi times d. So you get in total that Q prime is the convective coefficient times pi d times delta T. Now, what about the value of H? We know everything except H, but please pay attention for the unit, okay? If you want to use the exact unit of Q prime given, which is kilowatt per meter, so if Q prime is in kilowatt per meter, then the convective coefficient will be in kilowatt per meter square times, kilowatt per meter, yes, meter square Kelvin, okay, or degrees, it doesn't matter, because delta T in Kelvin is equal to delta T in degrees. So always pay attention for units. If you forgot the unit of H, it's fine, you can find it in a very simple way, because you know that when you write Q equal HA delta T, okay, Q will be in watt. So watt is equal to H times A times delta T. So to have the unit of watt, Q should be in watt per meter square times Kelvin or degrees here. So here, let us say degrees if we keep temperatures in degrees, okay? And if you want Q in kilowatt, then H will be in kilowatt per meter square degrees. So here all we did is we simplified by L both terms. So of course, H will remain for unit kilowatt per meter square Kelvin. Now, if you do exactly the same work for air, you can get the convective coefficient involved in air. And as expected, because Q prime needed to maintain a temperature, a constant temperature of the cylinder when exposed to air is equal to 400 watt per meter, while in case of water, the flux needed is 28 kilowatt per meter. We can just then compare the two convective coefficients. So we can find that in case of water, the convective coefficient is 4,570 watt per meter square Kelvin, while in case of air, it's equal to 65 watt per meter square Kelvin. And it is expected because to have much higher convective coefficient for water, because the power needed to maintain, if you want the temperature in this case, is much larger than the case of air. Since heat lost by convection with water is larger than heat lost by convection with air, then we need a much larger power to maintain a constant temperature when water is used. So we can deduce the following. In case you want to have heat loss, so let's say you have an application where you want to cool a fluid, then you will use water as a fluid for convection. However, in other application where you need to maintain a constant temperature or you want to reduce losses, then of course it's better to have this object in an environment with a fluid of air rather than having water around it. Any question on this?
Okay.
Okay, so let us do another problem. In the following temperature controller for closed dryer, it consists of a bimetallic switch mounted on an electrical heater attached to a wall-mounted insulation pad. The switch is set to open at 70 degrees, which is the maximum dryer air temperature. To operate the dryer at a lower air temperature, sufficient power is supplied to the heater such that the switch reaches a temperature of 70 degrees. When the air temperature T is less than Tsat. If the convection heat transfer coefficient between the air and the exposed switch surface of 30 millimeters square is 25 watt per meter square Kelvin, how much heater power PE is required when the desired dryer air temperature is T infinity equals to 50 degrees? So our purpose in this problem is to maintain a temperature of 70 degrees at this level. Okay, and we'll see that to do this, we can supply electrical power. So we supply electrical power. The electrical power will be like a source of heat if you want. So you will have generation of heat through your system. And this electrical heat, which was transformed to heat, then will be convected out to the environment. And we want to ensure that we keep a temperature of 70 degrees at the surface. So whenever they give you steady state values, so they tell you we want to ensure a set temperature of 70 degrees, this means that you don't have variation with time at this level. And because you don't have variation with time, whenever steady state assumptions take place, we can directly say that what is coming in to our system will go out. So we are giving energy to our system through heating form, because we are transforming electrical energy to heating energy. And then this energy is convected outside. It's lost by the system because of convection with air. So all we have to say then is that the electrical heat will be convected out, so is equal to Q convection. Okay, now the question is how much power is required? Okay, so just whenever we say power, so we are reasoning in watt unit, and we know that the convective flux in watt is given by H times A times delta T. Okay, so now we can say the following. All we have, it's a very simple equation, despite that the description of the problem seems a little bit complex, but in reality, physics is very simple. All we have to say is that the electricity current will produce energy. You know, if you want also, if they give you the voltage and the current, you can calculate this power, because the electrical power can be calculated as U times I, and also if they tell you it's a resistance, you can go into more details. You can say that the resistance here is R times I. So the power will be Ri squared, okay? So if they give you, for example, okay, don't worry, I don't expect from you to know these formulas, but in a problem, I can give you information and just you build the problem. So I can tell you that the power in a resistance can be calculated as Ri squared. And then, for example, what should be, if you have a resistance of, let's say 10 ohm, what should be the value of the current? So here, all we have to do is to set this balance of energy, because we don't have, energy is conserved, but it's just changing from one form to the other. It was first energy in the form of electricity, then it is transformed by Joule effect to heat, and then this heat is convected out. So we can write that the power of electricity is equal to HA times delta T. And then we are able now to find what is the value of the power given to our system. As usual, just pay attention for units, okay? So in case you want to have your power value in watts, then for your convective coefficient, you use watt per meter square Kelvin. As I told you before, for delta T, it doesn't matter if you use temperatures in degrees or in Kelvin, because delta T in degrees is exactly the same of delta T in Kelvin, since the difference between the two is a constant. You know that T in Kelvin is T in degrees plus 2,773, okay? So if you perform difference, it doesn't matter if you express your difference in degrees or in Kelvin, you will get exactly the same result since the constant effect will cancel out. Any question on this? Okay. These small problems will be a preparation for a much bigger problem. Okay, so in general, we might have several heat transfer processes involved in one problem. We'll do this in the last problem of this extra problem sheet, okay? Here also, it's a relatively simple problem. You have a spherical probe of 0.5 meter diameter that contains electronics that dissipate 150 watt. If the probe surface has an emissivity of 0.8 and the probe does not receive radiation from other surfaces, for example, from the sun, what is the surface temperature? If you remember in the course material, when we introduced radiation, we said that a surface will absorb and will emit heat by radiation. And we considered that we have an infinite surface surrounding the object, then the net radiative flux will be Q net equals to epsilon times sigma times area of the surface times T surface to the power 4 minus T infinity to the power 4. But please pay attention, when we applied this form, we assumed that we have a flux that is radiated, emitted from the surface and one that is absorbed by the surface. But in this problem, they are telling us that it's not receiving any radiation from other surface. So it's just emitting. Then we can say that the emitted flux is simply epsilon sigma A surface times T surface to the power 4. And we don't have to account for the absorbed or received flux, because they are saying that we are not receiving any radiative flux from other surface. We are just emitting heat by radiation. From the other hand, we have like a generation power within our system. Okay, so you have an internal source of generation. Here it's an electrical circuit. So it's from, if you want electrical power, you can have, for example, if you have combustion, another example in chemical engineering, you can have a combustion that is taking place, which is generating heat. And then this chemical heat that is from chemical source can be convected back by radiation effect. So can be, lost by radiation effect. And many times we don't have, as I said, one process. You might have several processes at the same time. So for example, if in addition to the emitted flux, they tell you we have forced convection, since we might have a flow that is passing over this body, and this flow is characterized by H and T infinity, then all you have to do is to do a small energy balance over a thin layer of your system at the control surface of your system. Why? Because you can say that all processes will take place over the external surface. So if I take a small control volume, okay, embedding the surface, I can say that the generated flux will be transmitted by conductive effect, okay, to the surface, and then from the surface, this heat can get out through radiation and convection. Okay, so through this thin layer, the generated energy will be transmitted by conduction in the material. So if we do a small analysis, we can say the following. We can say that the generated rate of energy will be transferred throughout our system, okay, through conductive effects. So it's equal to Q conduction. And this conductive flux will be transferred to the outer environment through radiation and convection. Here it's much more simpler because we don't have convection. They didn't mention that we have a flow over the system. So we can simply say that the generated flux will be lost by just radiation, which is Q emitted, and it's equal to epsilon times area of the surface times sigma times temperature of the surface to the power 4. Okay, so now in this equation, the only unknown is the surface temperature, so we can solve for it. In case we have, if you want, several mechanisms, we might have an equation of force order that is not very easy to solve numerically. It's fine. Then I just tell you, I don't ask then for the temperature. I just tell you, write the energy balance that will allow you to calculate the temperature of the surface, but no need to solve it. So whenever you have complex formula, don't worry about it. I just care for the final equation. You should know how to reach the final equation. And if it's complex to solve, you don't have to solve it. Let us move now to a more complex problem involving several processes. So we have here a long bus bar of cylindrical shape that is used to make electrical connection. It's characterized by a diameter d and is installed in a large conduit having a surface temperature of 30 degrees and in which the ambient air temperature is T infinity. So if we illustrate the problem here, we have a cylindrical rod. It's characterized by a certain diameter d. And it is installed in a large conduit having a surface temperature of T infinity. So you can consider that you can simulate this system as an infinite surface. And this surface, T infinity, so as I said first, that T wall, so you can consider that the surfaces of the conduit are characterized by a temperature of 30, and also air that is, so this will be for radiative flux, and also air that is between the conduit and the bus is also characterized by T infinity of 30 degrees. So we have here already, we can think about two types of heat transfer from the surface to the surrounding. We can have a part because we have a fluid surrounding it, so we have Q convection. And also because we have a large surface surrounding it, we'll have a flux of radiation. Now, they told us that the electrical resistivity of the bar material is a function of the temperature. So they gave us, if you want, the property, the electrical resistivity rho is function of the temperature. So we'll find this value in order to calculate the power, the electrical power that is generated within our system. So the electrical resistivity is given function of temperature, and we have that T0, which is the temperature here in this formula, is equal to, which is a reference temperature, is equal to 25 degrees. If we do an analysis here, larger is T, larger will be the electrical resistivity. Okay, the bar experiences free convection in the ambient air, and the convection coefficient depends on the bar diameter, as well as on the difference between the surface and ambient temperatures. So here, in general, they can give you a convective coefficient directly, or they can give you an empirical equation, an empirical formula that will allow you to calculate the convective coefficient. This is the case here. Okay, if you remember in the course material, we determined several ways of finding H. So in general, we give empirical relations. We give, for example, the Nusselt number, and from Nusselt number, we can calculate H. Other times, they can directly give us H, or like here, they give you the equation allowing you to calculate H. So here, H, as we can see, is a function of a constant, which is provided. So C is 1.21. It's function of the diameter of the rod, and also is function of the value of delta T. And the emissivity of the bar epsilon is provided. Now, recognizing that the electrical resistance per unit length for the bar is R prime E equal to the electrical resistivity, which is given over AC, where AC is the cross-sectional area of our cylinder. We want to calculate the current carrying capacity of a 20 millimeter diameter bus bar if its temperature is not to exceed 65 degrees. So as we can see, the purpose is to maintain our rod surface temperature at 65 degrees. This is our purpose. And we want to compare the importance of heat transfer by free convection and radiation exchange. So first, as we said, we should identify the different processes of heat that are involved in this problem. Okay, so first we can say that we have, as we mentioned already, we have heat loss by convection and by radiation. And we know the expression of this rate of exchange. We know that Q convection can be calculated as H times A times delta T. And because the analysis will be, as you can see here, they are giving us the resistance per unit length. So we can conduct all the analysis per unit length here. They didn't give us the length of the bar. And it doesn't matter for us because we have constant properties per unit length. So we can express all our fluxes per unit length. So we start to say a Q convection per unit length, or we can just use the symbol of Q prime convection is equal to Q convection over L. Again, the area is of exchange by convection is 2 pi R times L. So L will cancel out. And delta T is simply the temperature at the surface minus T, which is minus the surrounding temperature, which is 30 degrees. Okay, so we have T of surface 65, we have the air temperature 30. And concerning the convective coefficient, we can calculate it from the following empirical relation. So they gave us C. Okay, we know the value of C. Concerning D, we'll see that D will cancel out here. Okay, so in case not, it should be given. So let me check if they gave us D. Okay, look, if they don't, yes, they gave us D. If they don't give it, okay, we can keep the expression function of D, and in case it will simplify, then we can come up with numbers. So here we just replace D by 20 millimeter. And as usual, pay attention for units. Convert everything to conventional SI units. So use DN, use DN meter, because as you can see here, when they gave you this empirical relation, the unit of C is watt per meter to the power minus 1.75 times Kelvin to the power minus 1.725. This means that D that is used in this formula should be expressed in meter. And as we mentioned before, delta T is in Kelvin, but it's fine if you express it in degrees because the value is the same of delta T in Kelvin and in degrees. So now the first step will be to calculate H by just replacing C by 1.21, replacing D by 20 times 10 to the power minus 3, and replacing delta T by 65 minus 30, so 35. Once we get the convective coefficient, we are ready to calculate Q prime convection. So Q prime convection is simply H pi D times delta T. And as we mentioned, the first step will be to write the energy balance. So energy N, which is due to electrical power, minus energy out, we have here to determine if we have energy N or not. Here, if you want, you have just generation of energy and you don't have fluxes if you want that are coming in or to the system. You are just having fluxes getting out. So E dot N is 0 in this problem, okay? How it can be different than 0 if you have absorption, for example, of heat from outside environment. Okay, so here we can just say that we have the convective flux, we have the net radiative flux, and we have the generation within the system. If you want, radiation can be considered as a net. When I'm talking about radiation, I'm talking about net value. This is why I considered it as E dot out. But if you want to decompose it into details, you can say that the net radiative flux is due to one flux that is absorbed and another one that is emitted. But here we are, since we are just considering the net value, we are treating it as an outward flux. Okay, so we can say that minus Q prime radiation minus Q prime convective, because they are getting out of the system, plus the generated flux is equal to 0. Now, why this generated flux can be written as I square R prime? As we mentioned already together, the power from electric current is U times I, which is Ri square, okay? But this value will be for a certain length. If you are doing the analysis per unit length, then P over L will be equal to R over L times Ri square. So we divide the total resistance value by the length involved times I square. In this problem, they gave us already R over L, because R over L is the resistance per unit length, and it's given to be equal to the electrical resistivity over the cross-sectional area of the rod. So we can replace here R over L by R prime electric, and R prime electric is equal to rho electric over the cross-sectional area is pi d square over 4 or pi r square. We have the radius of the rod, we replace it. Now concerning rho, it's given also, it's given function of temperature. Okay, so alpha is a constant given, and just to find the electrical resistivity, we have to replace T by 25, T0 by 25, and T represent here the ambient air temperature. So we can just, no, one thing, look, here the bar material is a function of temperature. So we have the temperature of the bar. Here we should replace T by 65 because the electrical resistivity is related to the temperature of the material. that we are using. And here we are considering, we are treating it as given. So we have the rod temperature should not exceed 65 degrees. Since we are working in steady state conditions, we are assuming to have a value of 65 for the rod. So we can replace T for the rod by 65 degrees. And then we'll be able to calculate the value of R prime E. And once we calculate R prime, we can say that the value of power per unit length is R prime times I square. Okay, so now if we write our equation, we are ready to replace all terms. By replacement, we can find that the value of the electrical power the per unit length, which is I square R prime I, is equal to the following value. Okay, and here they didn't give us the value of I. So if we want to calculate I, we should be, if you want, we should have already performed the calculation. We can get the value of R prime square I, since we have R prime E. Once we get R prime E from our calculation here, we can deduce the value of the current. Okay, so because the only unknown in this equation is I, since they provided us with all information, we have the emissivity, we have the diameter of the rod, this is the Boltzmann constant, we have the temperature of the rod, which is 65, and we have the temperature of the surrounding. We have also the convective coefficient from the empirical formula here. So we have everything except the current, because here we express the power as R prime E times I square. R prime E can be calculated, and from the energy balance, we can calculate the total electrical power per unit length. And then the only unknown here will be I. We can calculate the value of I. Okay. Now, if you want to compare the relative importance of heat transfer by free convection and radiation exchange, what should we do? Who can tell me how we can answer this question? What do they mean by compare the relative importance of heat transfer by convection and radiation exchange? Look, I will, the time will end. I will open a new session to continue, okay?
Okay.